welcome to this series of case studies and experiments using PicoScope. That's PicoScope software and also NVH as well, so that's in the Pico Diagnostics software. It really follows cases that I feel no other tool would have got us out of trouble, would have helped us diagnose conclusively what the problem was. In some cases, you don't end up with a diagnosis. You know exactly the depth of repair required, and to actually repair is beyond economical repair. Nevertheless, you've got that evidence that stops those awful incidents happening where it's an awkward discussion or it just becomes a scrap vehicle. In most cases, or it can be that is the case. Okay, moving on to ABS, one of four, I think, ABS case studies we've got here. This is the first one. This is an Audi A4 all-road, and this is involuntary operation of ABS with no fault codes. And this is quite a common pattern with ABS. You'll notice that when you come to a halt or driving at very low speeds, manoeuvring the vehicle, that when applying the brake, all of a sudden there's a kickback from the pedal, sometimes accompanied with a pump operation underneath the bonnet. So here we have 4 ABS wheel speed sensors, that's channels A, B, C and D. And we can see what is square waveform. So first impressions, the signal looks present, all looks good. It doesn't look like there's any shorting, any what we call sporadic sort of signalling, until we apply a math channel. Now if you look further down, we've got frequency A, B, C and D. So we are graphing the frequency now of the square wave signal, so graphing the frequency of the raw data. And it does become apparent very quickly that what looks to be at least every revolution, or certainly at specific events during the wheel rotation, there is an event where the frequency changes abruptly. And that doesn't appear that obvious when you actually look at the raw data in Scope View 1, in Scope View 1. We see there that, again, it looks okay. And well, I guess if you look closely, you can see that the spacing between these two pulses does differ from the spaces above. So on channels A, B and C, pretty much sequential, and then on D there is a difference, but I think you need a keen eye to spot that. When you actually apply frequency math channel, you can see it straight away. And when we zoom in on the frequency math channel, this is in Scope View 3, we can see we've got this sort of uniformity, then followed by this drop in frequency, sporadic increase, and then drop again. So here we're using 3 scope views, raw data, the math channel and the zoom to help us locate why this is occurring. And hopefully, yeah, you'll see it there in the next slide. Image on the left is the wheel bearing from the Audi A4. You can see there that the encoder ring, the magnetic pole ring, how we've got a segment that's broken. And that was giving us that additional sort of spike in the frequency math channel every revolution of the wheel. And you are committing to a reasonable repair, and without real data to support your diagnosis and provide evidence to either warranty or the customer, you really are out on a whim. On the subject of these encoder rings is how could we have possibly checked the mechanical integrity of the encoder ring without removing it and using something like this field finder. We have used a technique in the past. This was on a Mazda on the image on the right here. We used our keyless entry detector. If you actually take the ABS wheel speed sensor out of the hub and insert the keyless entry detector into the hub where access permits, it's not always possible. It behaves like an inductive sensor, so you can then rotate the wheel and just looking for even pulsations, even segments. You should end up with what is effectively a sine wave, but without any interruption. Had we used this technique on this encoder ring on the left, we would have seen that event. Nevertheless, going on the math channel from the vehicle actually driving on the road, we had all the evidence we needed. So a little tip there, but something that you can use maybe going forward. If our keyless entry detector is too large to actually go into the ABS sensor aperture, then some kind of inductive device, coil wrapped around an iron core. I'm sure you could get something from that you can then use the features of PicoScope to display the pulsations. Just a quick word on the channel B here. This is 1 pulse per revolution, and this is using the optical sensor. So normally available with our MVH, but you can buy that separately. And that's just a piece of reflective tape on the wheel, so that every time the wheel turns 1 revolution, we get 1 pulse. And we know between those pulses that we've completed 1 revolution, so then we can examine the teeth or the magnetic pole ring on the wheel bearing, and determine whether or not there's an error there. So it's a nice tip. And just interestingly, what I'm finding patterns wise is that typically there's 48 teeth per wheel speed sensor. I wouldn't take that as gospel on every vehicle, but a lot of vehicles that I've worked with, 48, this number 48, so that's 48 teeth or 48 magnetic poles. It is a value that keeps coming up time and time again. Okay, that's it. Thank you for watching, and any questions, please send them over, and we'll endeavour to answer them as ever. All right, take care.